Okay, so welcome back everyone to the final day of the event. Mario's going to continue the second part of his mini course.
Yeah, thank you, Jethro. So let me recap what we did the other day. The other day in part 1, we started with a linear algebra with invariant pairing, a quadratic Lie algebra, and defined some equations which were algebraic equations, nonlinear, depending on an endomorphism of G, which was square into the identity, and it was orthogonal with respect to the pairing, and says that this was non-degenerate. In the examples, it was actually positive definite, this quantity. And also an element in G duo identified with G via the ambient pairing. And from this, we define equations for spinors, which had this form. It was some sort of spin connection constructed from this data G and phi, acting on the spinor was 0, and then also a Dirac type operator equals to 0. So the goal today, hopefully I managed to show you, convince you that there is an interesting story about these equations in relation to the existence of solutions and also moduli spaces. And the goal of today is to show you, to give you evidence of some sort of, it's a general expectation. I would like to convince you that from solutions of the Killing and spinor equations, from a solution of the Killing and spinor equations, one can construct an embedding of a suitable vertex algebra into some ambient vertex algebras, or representations of suitable vertex algebras, which are interesting and come from string theory. Typically, they arise as the chiral algebras of two-dimensional sigma models. And this is some sort of baby version or algebraic version of a lot of work that has been done over the years by many people, including Raimundo Helwani and collaborators, on constructing embeddings of suitable vertex algebras into a sheaf of vertex algebras over a manifold called the chiral Aldebaran complex. Anyway, so let me start. So today I have to do some reverse direction. So I'm going to start from some geometry and hopefully convince you that this produces interesting algebras. And these algebras, or this is the way I first learned about something related to vertex algebras. Let me start with something called current algebras, which was studied by Alessia and Strabo from the theory of two-dimensional sigma models. So let me start with something geometric. I consider a sigma model, which is a physical theory where the fields are maps from a surface, so a two-dimensional smooth manifold, into some manifold M, and this manifold M is endowed with two tensors, a metric, which may have arbitrary signature, but in principle we could take it Riemannian, and a B field, a 2-4. And on the surface we also put a metric which for physical applications will be Lorentzian. It will be of signature 1-1. So here one constructs this action. So one constructs a natural energy functional for these maps from the surface into the manifold, which has this form. And then morally, you have to think of as critical points as trajectories of loops in the manifold, trajectories of strings. Okay. So the surface, which I'm going to think of as a cylinder, is going to be the worldsheet of the string propagating in the ambient, in the target manifold. So one way to think of this functional, which looks a bit, I don't know, maybe arbitrary. I mean, the first part is pretty natural. It's just the energy of the map. The second part may look a bit random. So there is this notion of magnetic geodesic on a Riemannian manifold. So you fix a Riemannian manifold, and then if there is no, I mean, if we're trying to do something like a theory of gravitation, if there is no further matter or fields in the theory, then the point particles will move by trajectories given by geodesics, which are minimizers of this energy functional here. But if we have a magnetic field, dA, for a one-form potential, then the trajectories will deform in this, using or following this type of Lagrangian. Okay? Any questions so far? Okay, so we start with this, and then, yeah.
Like an example, the endpoints of the interval, they'll be fixed.
Yeah. Let's put them fixed. Yeah. I mean, you can make this as complicated as you want, but let's put them fixed. I mean, this is just motivation for what is coming later. So you can take the time of extremizing the functional. You put this. You take now a cylinder and take the Minkowski metric. I'm going to sit here because this is. So you take a cylinder with this metric, Minkowski metric, and then extremize. And what you get is some sort of deformed wave function equation. Okay? I mean, think of the Riemannian setup. In the Riemannian setup, the energy of a map has critical points given by the Laplacian. Right? If we are in Minkowski signature, then what you get is the wave equation. And what we know about the wave equation from the undergrad is that to fix a solution of the wave equation, what you need is to prescribe the boundary conditions and to prescribe the tangent vector at the boundary conditions. So the moduli space of critical points is going to be given by maps from the boundary of the surface, which is two copies of S1, into the cotangent or the tangent of M, which fixes the value along the boundary of the surface, and also a first derivative. Okay. So this loop space of the cotangent can be thought of as a moduli space of classical trajectories in this two-dimensional sigma model. And usually, when you are doing field theory, moduli spaces of the classical field equations are symplectic. This is like a general law. And here we can even describe very explicitly what is the symplectic structure. The symplectic structure. So first, what is a tangent vector to the loop space of the cotangent? This is just a vector field along the trajectory where you are. So we fix a loop in the cotangent, so a map from the circle into the cotangent, and then a vector field along that is a map from S1 to the pullback of the tangent of the cotangent. And then you can cook up this symplectic structure, which is given by coupling the symplectic structure just on the cotangent of the manifold, the standard symplectic structure. You pair this with these two variations given by tangent vectors along the map. And it has this correction, which is like doing some sort of, how do you call this? Like a magnetic, I always forget about this name. Anyway, so if you have a fibration and you have a symplectic structure on the base and a symplectic structure on the total space, you can always pull back from the base and multiply by a factor, and this is what appears here. So more generally, you see this formula, even though the functional doesn't make sense, but this formula really makes sense for any closed free form. You can put the same thing, and you will get some sort of, morally, you will get some sort of pre-quantization on some sort of line bundle over the loop space where this is the symplectic structure. Okay, so we can ask the question of what is the quantization of this moduli space, right? This is a symplectic manifold, formally at least, and we can ask ourselves, is there a a natural quantization. This is, of course, formal, and people who do quantization, like Alejandro Cabrera, for example, who is not here, know that typically if you have a symplectic manifold, the family of functions that you can quantize is not all the possible functions. You need some special functions in order to quantize. Not all functions are quantizable. Typically, you need some more information. You need a special class of functions. Well, in this nice paper, Alexeyev and Strabo proved that there is a natural class of functions on the loop space of the cotangent which can be quantized. One can understand what happens with them. And these are given by something interesting. These functions are parameterized by smooth functions on the manifold I started with, and sections of the tangent plus the cotangent of a manifold. Okay? And before I go into details, well, first, let me say two things. If you go into this paper, which is beautiful and has very interesting ideas, it's hard to understand because it's written in a very physical way. And then there is a nice paper by two physicists, Sabsin and Ekstrand, which write down this paper in a mathematical way. It's kind of funny, but this is what happens. So I recommend you to read this paper, and on the side, read the paper by Sabsin and Ekstrand, which is very clear. So just to make contact with this thing we were talking the other day about, you will see immediately that this space of special functions, parameterized by functions and sections of tangent plus cotangent, automatically makes contact with the thing we were talking about the other day. In the following sense, so if I take my M to be a compact Lie group, or a Lie group, then I can take the corresponding space. Let me write it with a K plus sections of T, K plus T star K. And what I can do is to take, for example, right invariant functions and right invariant sections. If I do that, then of course functions are just real numbers. And this is going to be just by the Lie algebra plus the dual of the Lie algebra, which is what I was calling the other day G with the ambient pairing, with the indifferent pairing. And you see that this even morally has the information about the pairing given by duality, right? So this simple class of functions actually makes contact with the type of object we were dealing with the other day, which is a quadratic Lie algebra. Okay, so how do you construct functions in the loop space of the cotangent out of this? I mean, there is one which is very simple, which is this thing, right? I'm going to fix a volume form on the circle. So if I have a map to the cotangent of M, which covers a map from the circle into M, I can construct this function, which is at the map, depends on the function of M, and it just takes the integral over N of the pullback of F times the volume. Okay, this is a very simple expression. And if I have a vector field, I can do something similar. I can just the vector field is on the target, so I can just evaluate the vector field against P, which takes values in the cotangent, right? And this gives me a function, and again, I integrate along the circle. And the third possibility is I take a one form, a section of the cotangent, and then what I do is I take X, which is the map that P covers. I take the differential that takes values in Tm, and I pair with alpha, and I integrate along the circle. Okay, so there are these three classes, natural classes of functions, which appear. And surprisingly, or at least, I mean, it was nice when I read this. Oh, I'm going in the wrong direction. So Alexeyev and Strabo, part of the thing that they do is to be able to calculate the Poisson brackets with respect to this symplectic structure that I told you. And they find something remarkable. So the Poisson bracket of as two sections of tangent plus cotangent, which I denote E1, E2. So E is a vector field plus a 1,4, is given by the corresponding function on the loop space of the cotangent, given by this bracket, which is called the Dorfman bracket. And if you again do the work, this is an exercise, do the work of taking this expression and putting this expression into a Lie group, you will see that you find precisely the Lie bracket that I presented you in the previous lecture. Okay? And also, if you do the Poisson bracket of one of these functions determined by a section of t plus t star with a function given by a function on the manifold, you get the other information that you need to construct something called a Coulomb algebroid, which is the projection from t plus t star into t, which is called the anchor map. Okay, so this also comes naturally, if you want to think of this algebraic setup, this also comes naturally equipped with a map into K, which is just a projection. Okay. Okay, so far so good. But we were thinking of quantization, and what they noticed, and this is the key of the story, I guess, is that these functions are special. They are not random functions. We are doing some sort of field theory, and in field theory, the fields and everything acquire some sort of distributional nature. So what they observe is that because these functions are given by integrals, you can always insert a test function on the expression of the function, right? So you can take this thing here, for example. Oh, sorry. You can take this function here and insert in the integral epsilon, and epsilon is a smooth function on the circle, right? So this becomes now a function in the loop space of the cotangent with values in distributions on the circle. And this way, doing this sort of formal insertion of the test function, they were able to calculate something that they call a current algebra. It's like a Poisson, it's like the Poisson bracket, but thinking that it takes values in distributions. And they call this a current algebra. And remarkably, the only piece of information that we were missing in the previous picture was the pairing appears when you do this distributional bracket. So if you do the distributional bracket of two of these J's, these currents, determined by sections of t plus t star, you get the previous semi-classical expression, so the current corresponding to the Dorfman bracket, plus the distributional derivative of the J corresponding to the function given by the pairing of the two sections of t plus t star. Okay, so I give you two sections of t plus t star. So this is a key idea. So I give you two sections of t plus t star. Associated to this, I tell you that I have some GAAG. I have functions. Sorry, I have functions in the loop space of the cotangent of M, formally, but with values in distributions on the circle. And then when I do the bracket of these two things, there is an argument which tells you that you can identify this distributional bracket with another element of the same sort, a function on the loop space of the cotangent with values in distributions, which is given by G of the Dorfman bracket. The Dorfman bracket in this setup is just the natural Lie algebra bracket that I have here, plus the distributional derivative of the current given by the function given by the pairing of E1 and E2. Okay? So this suggests, and yeah, the other the other doesn't change. So this one doesn't receive any correction. So anyway, so this suggests that naturally associated with two-dimensional sigma models, there is a class of algebras which are some sort of quantum. And one can now be a bit more precise and ask what is the quantization, but in the sense of the formation quantization of this current algebra. Okay? So formally or morally, the answer to this question, what is the deformation quantization of this type of algebras, is vertex algebras. Okay? And now I'm going to start with the actual thing. Maybe I can, no, let me start here. So what are vertex algebras? So so some of the main experts in vertex algebras are here. So if I say something that you don't like, please correct me. I'm happy to take back. So vertex algebras. Before I start, are there any questions about this part? So I fix a vector space, which may be infinite dimensional. And it's going to be over a field, but I'm going to think typically that it's going to be over C. And then a formal distribution is given by an expression of the form AZ equals sum with n in Z of an Z to the minus n minus 1, where the ans are in endomorphisms of V. And I'm going to say that a formal distribution is a quantum field if for all V in V, there exists a big N such that A and V is 0 for all n bigger than N. So it means that when I get very negative powers of Z, then any vector is annihilated up to a suitable point. Okay, and this N may depend on the vector. It may be different from vector to vector. For quantum fields, I can define what it means for them to be mutually local. Definition. For AZ, BZ quantum fields, I say that they are mutually local if there exists n big such that Z minus W to the n and AZ BW is 0. Okay, so this expression is kind of weird, but let me make a small comment about this. So firstly, this comes from thinking of this type of objects as formalizing two-dimensional quantum field theories. And quantum field theories are relativistic. So here we have a variable Z, which is, we think of it as a sort of complex variable, but I should think really as Z as after doing weak rotation. So I should think really as living in a cylinder. Okay? And when you do that, this type of expression comes from the notion of causality. Here, it comes from some sort of notion of locality, in the sense that what this means, I have to think of this AZ and BW as fields living on a surface where the coordinate set is the coordinate on the surface, and localized at points. And this expression here means that the commutator of two fields AZ and BW, I have to take them in different coordinates because these are going to have distributional nature, so I cannot otherwise multiply. So in the coordinate Z and W, as before the currents, this is going to have some sort of distributional nature. But if I take them in two different variables and I do the commutator is going to be localized at the diagonal Z equals to W. Okay? So this means that morally, this expression here is only going to depend on the delta function Z equals W and derivatives of the delta function Z equals W. Okay? Okay, so what is a vertex algebra with these ingredients? A vertex algebra is a tuple V vacuum T F, where V is a vector space. As before, this object called the vacuum is a non-zero vector. T is an endomorphism. Which, we'll say the axioms later. And then the most weird part of the definition is this thing that you have a family of quantum fields which are mutually local. F is a family of quantum fields which are pairwise local. One with each other. And from the field theory point of view, this means that they will preserve causality. From this point of view, it means that these commutator brackets are localized formally in the diagonal Z equals W. Okay, so this should satisfy some axioms, which are, well, firstly, the endomorphism is going to annihilate the vacuum. I already said this thing, but anyway, AZ, BZ in F, then they are mutually local. And finally, here I'm missing one thing, which is T commutator with AZ is the same as taking derivative with respect to Z of AZ. Sorry. And finally, some sort of completeness property that B is spanned by these endomorphisms which appear in the family, which are called Fourier modes, applied to the vacuum. So if you have like A1, AK, and K. So these are any K tuples for arbitrary K, but finite, of elements in the family of quantum fields, and this applies to the vacuum, this generates V. Okay. So the first thing, because this is if the first time you see this is a very weird looking definition. Let me give you an example, which is the first example you should think of, which is sometimes called the Heisenberg vertex algebra or free boson. So you take the vector space, I'm going to call it H, is polynomials in infinite many variables. The polynomials are finite, okay? But finite sums of monomials in infinite many variables. Sometimes this is called the Fock space. And then I take, for n in Z, positive, I'm going to define an endomorphism here, which is h minus n is going to be multiplication by xn. H0 is 0, and hn for n positive is n partial xn. So taking derivatives and multiplying by n. So typically these are called creation operators, and these are called annihilation operators. And then you form an infinite series of the form sum with n in Z, hn, Z to the minus n minus 1. And you can check that this is actually a quantum field. This is yeah. So what else? So one exercise that you can do is to get familiar with these expressions, is to check that if you take Z minus W squared to HZ HW, this gives you 0. So you just formally multiply the series in Z coordinate with the series in W coordinate, do the commutator, and you will see that this is annihilated by taking Z minus W multiplying. And in this setup, we can set the vacuum to be 1 in the polynomial algebra, and this T operator to be 1/2 of sum with k in Z of hk h to the minus k. And this satisfies the axioms.
-1 minus k?
Yeah, sorry. Yeah, sorry. This is the, otherwise you need to use the denominator. -1 minus k, yeah. With the case you put 0 here, is something funny appears, which is very important for the theory, but I don't have to comment on. But this case is very simple. You can check that these operators are, I mean, this is a well-defined operator. It makes sense. Okay, so this is one example. Let me give you another example, which is important for us, even though it will appear in a different disguise later. Which is the affine GAAG-Moody. So you take G with a pairing, a quadratic Lie algebra, as we had before. And then consider G hat to be the loop algebra plus C, so a central extension of the loop algebra, with the following, this is like the loop algebra. With the following bracket. So this is a Lie algebra with bracket given by the following expression. So A T M B T N is the bracket of A B T to the N plus M plus M delta M minus M AB, and that's it. You can check that. I mean, this is obviously skew symmetric, right? And you can check that it satisfies Jacobi. And C commutes with everything. Okay, so this is central. And then you can form something called the vacuum model, which works as follows. So you first define a subalgebra, which is given by J hat plus, which is given by GT plus C inside G hat. And then for K in C, you define the so-called vacuum model, which is given by taking, this is VKG, which is given by the universal enveloping algebra of G hat, tensor with C, I mean a vector space generated by just one element, we can go to call the vacuum, over the universal enveloping algebra of G hat plus. And here, I'm going to prescribe the action of this to be GT is going to act as 0 on the vacuum, and J1 is going to act as K in the universal enveloping algebra. Okay? So what is this doing for you? What occurs here is that whenever you have an element in the universal enveloping algebra, if you have something on the right which has positive powers of t, this is going to annihilate the vacuum, right? So you can always modify the expression of your element in the universal enveloping algebra so that all elements in this model appear as negative powers in T multiplying the vacuum element. And this has, okay, so this is for the vector space underlying this vertex algebra, but there are, of course, a family of quantum fields, which is defined as follows. For any element in G, you take a set to be the sum with any set of A Tn set minus n minus 1. And again, you can try to check. It's hard because I'm not giving really any details, but you can by hand go and check that. Again, Z minus W squared AZ BZ is again 0. Sorry? Oh, yeah, sorry. Yeah, thanks. Yeah, otherwise it doesn't make any sense. So these are bilateral series, so it doesn't make sense to multiply bilateral series in the same variable, but if you put two different variables, this is fine. Right? This is what we are playing with. And yeah, and the last piece of information that you need is that T is actually determined, completely determined by the axioms. So this is again an example of vertex algebra. Okay, so how much time do I have? 45 minutes. Okay. Okay, so I need two pieces of information for the application that I'm going to talk about. One is an important theorem, which probably is due to GAAGs, but the experts can correct me. Is that, well, first, let me explain something. Let me explain something because otherwise this doesn't make any sense. So if we take on a vertex algebra, I can take one of these quantum fields and apply it to the vacuum. And this will have an expression of the form sum m in z, vn, z to the n. And the axiom T AZ partial z AZ, what this is telling you now in terms of the coefficients is that, let me not mess up with the coefficients, T Vn is n plus 1 Vn plus 1. But we also know that because these are quantum fields, we also know that Vn needs to be 0 for all n very negative, right? So what this tells me is that all the Vn's with n negative need to be 0. So what this means is that when I apply one of the quantum fields in the family to the vacuum, it makes sense to take the limit z equals to 0. Okay, so it makes sense to take the limit z goes to 0. And this gives me a well-defined element in the vector space V. So what this means is that there exists a well-defined limit when z goes to 0 of AZ applied to the vacuum for any element AZ in the family of quantum fields. So now the theorem, which I'm going to state informally, is that given V TF a vertex algebra, there exists a completion f bar of f. So it means that some family of bilateral series which are quantum fields, etc., which contains f. So this family f bar is going to be given by quantum fields which are mutually local, and satisfy furthermore the axiom TAZ equals partial z AZ, such that the map that I'm going to call S from F bar into V, which takes AZ to this limit, applied to the vacuum, is a bijection. It's a bijection. And the inverse of this map, I'm going to call it a state field correspondence. So the inverse Y from V to F bar, which takes an element A and promotes it to a quantum field it's called the state field correspondence. A state for elements in the vector space, and these are the fields. So in particular, if I have a vertex algebra, I can replace my original family of quantum fields. I mean, the first definition that I gave is good for like generating in a finite way the vertex algebra. But then what I can do by this theorem is that no longer work with the original family, but replace by this completion, and now I can promote any vector to a field. So in particular, what this tells me is that for any n in Z, I have a corresponding an and any a in V. I have a corresponding an in endomorphisms of V. So I have to think of as vertex algebra, on a vertex algebra as giving me, it's like an algebra with a Z worth of products satisfying suitable axioms. And for what comes next, I'm going to make the following definition, which is the formal replacement of the distributional bracket that we found in Alexeyev's trouble. So given A and B in my vertex algebra, I define the lambda bracket of these two fields, of these two vectors, sorry, as A lambda V equals sum with n bigger or equal than 0 of A n V lambda n divided by n factorial. Okay, so if you look at the expression, what this is doing for you, sometimes people, I mean, in physics, these are also called as the OPE, operator product expansion. What this bracket is doing for you is encapsulating the singular part of this state field correspondence, right? The powers, the negative powers of Z. Okay, so now I'm back to my slides. I don't know if you have any questions. This is a super short introduction to vertex algebra. This is a very delicate and important topic, and I do not pretend that you digest everything, but at least that you get a feeling of what is going on. Okay, so what are the formal properties which are satisfied by this lambda bracket? So we have now given a vertex algebra, we have found this special expression, this bracket, which is more finite in a sense, and it is encoding the singular part of the end products, which are these ANs. So the formal properties of the lambda bracket are summarized in this definition here, which is due to GAAG, I guess, and is the notion of Lie conformal algebra. As I said, this is a formal replacement of the notion of carbon algebra that it's a broader generalization, really. So a Lie conformal algebra is going to be given by a CT module, R, so a vector space with an endomorphism, which is typically going to be set to graded, and T is going to preserve parity. And I'm going to have a bracket which takes values in polynomials this is wrong, it should be C lambda, sorry. Polynomials in lambda, which satisfies these axioms here. So the T is going to spit out a lambda on top in the first entry, etc. Maybe the most complicated one is probably this thing here. So I mean, let me go to the second axiom. So A lambda B is not skew symmetric, but to find what is the corresponding skew symmetric expression, what you should do is you do B A in some other variable mu. You find the expression for the bracket, and then you substitute in mu minus lambda minus T. Okay, and this should give you A lambda B back. And this norm A, norm B are just the parity for homogeneous elements. Okay, so this is just expressed in terms of homogeneous elements. And for the last expression, you do something similar. Like you first do the lambda bracket in a formal variable, and then you substitute the variable which is in the subscript. The important thing for the rest of this talk is that there is some sort of formal quantization of Lie conformal algebras, which recover a Lie algebra, a vertex algebra in a universal way. So the theorem by GAAG is that associated to any such Lie conformal algebra, so in particular, just to clarify, in particular, given any vertex algebra, I find a Lie conformal algebra of this form by taking the lambda bracket. And now what this is telling me is that if I give you a Lie conformal algebra, then I can produce a vertex algebra, which is going to be called the universal enveloping vertex algebra, such that when I do the state field correspondence to elements in the image of R, this is going to recover the lambda bracket in terms of the end products. Okay? And in this setup, there is a product which plays a distinguished role, which is this -1 product. And if you remember my previous picture, or the original picture that I started with, about the current algebras, this -1 product is precisely the deformation quantization of the commutative product in the loop space that I was talking about. Okay? So it's a formal replacement for that. So this is why this is playing a distinguished role. This lambda bracket is like the distributional Poisson bracket, while the -1 product, which I'm going to denote with these dots, is the deformation quantization formally. Okay, some examples that you can produce out of this. So the Virasoro vertex algebra, and it's a pity to present Virasoro in this form, because you don't see it very explicitly, but this is what is good for the rest of time that I have. So to produce the Virasoro vertex algebra, which plays a key role in the theory of vertex algebras, you can take this Lie conformal algebra. So you take a vector space generated by one element, the corresponding CT module, given by tensoring by CT, and then a non-trivial lambda bracket given by this formula here. L lambda L is T plus 2 lambda L plus C lambda cube divided by 12. And then the Virasoro vertex algebra with central charge C, which is this number which appears in this in the scalar part of this expression, is given via the universal construction by GAAG associated to this Lie conformal algebra. Okay, one easy check that you can try to do with the previous axioms is try to prove that this is actually a Lie conformal algebra. This is a very easy exercise. Okay, so this is another construction of the Virasoro, which actually relates to the Virasoro-Lie algebra, but let me not go through that unless you. This is why I'm saying that. I mean, Virasoro is something which appears from infinite dimensional Lie algebra, which is very interesting. It's a central extension of the algebra of vector fields on the circle, but let me not go into that. Another algebra which is going to be important for us is Nouveau-Schwarz, or n equals to 1, which is now generated by two fields, L and G. L is going to be even, and G is going to be odd. And there are the following non-trivial lambda brackets for some choice of C in the complex numbers. So the first one is telling you that L satisfies the relations of Virasoro, so it's a Virasoro field. And then this other expression is something which also has to do with the general theory for vertex algebras. This expression is telling you that G is primary of conformal weight 3/2. And then there is this extra lambda bracket for G. And now, again, the Nouveau-Schwarz vertex algebra with central charge C is given by the universal construction applied to this Lie conformal algebra. So, I mean, as you see, I mean, of course, this reconstruction theorem or this extension theorem by GAAG is very powerful and encapsulates all the theory of vertex algebras into this simple Lie conformal algebras and some complicated set of properties. And finally, this is the last vertex algebra I need to recall for you. Now the n equals to 2 vertex algebra is given by 4 generators, L, J, G plus minus. L is going to be Virasoro, J is going to be even, and these G plus minus are odd. And the lambda brackets are given by this. So again, J is going to be a primary of conformal weight 1. These are primary of conformal weight 3/2, sorry. And there is a further expression. So one important thing here is that J is a copy of the free boson inside the n equals to 2. And this is something which plays a role in several parts of the story. Yes?
The lambda bracket for J doesn't have a J on the right-hand side.
Oh, yeah, sorry, yeah. Yeah, sure. Yeah, thank you. Anyway, so yeah, otherwise it wouldn't be a free boson. Yeah. So one important or one motivation for this particular vertex algebra is that it is somehow on the back of most of the phenomenon that appears in mirror symmetry. So when physicists think of mirror symmetry, at least originally when they started looking at this duality in string theory, they realized that mirror symmetry can be formally thought of as an involution in this vertex algebra, which takes L to L, J to J, and exchanges the G plus and G minus with a sign. And finally, this is the other algebra that I need. It's an extension of the affine vertex algebra that I presented before with this vacuum model. So you are going to take a quadratic Lie algebra, consider the Lie conformal algebra generated by G and G with odd parity and central element, sorry, a copy of C. And these are the lambda brackets which generate this thing. So if you see, this first part is this first part is generating a copy of the affine Kac-Moody inside the thing. Okay, so let me go now for the applications. So we started the other day with this construction of these Killing-Spinor equations and some properties of them. And my point now, or what I want to show you, is that Killing-Spinor equations are an object which very much interact, solutions of Killing spinor equations are an object which very much interact with the representation theory for Vertex algebras, in the sense that they produce natural embeddings of, in this case, the n equals to 2, but you can also try with other algebras into models. In our case, the model is going to be the superaffinization. So I start with a quadratic Lie algebra, G, and then recall from the previous day that given a triple G phi eta, where G is a metric on G, so a decomposition into orthogonal subspaces B plus and B minus, where the metric is non-degenerate. Phi is going to be, now I'm going to take it as an element in B plus. You can take it as an element in G, but then you have to project all the expressions, so it doesn't matter. And eta is a spinor, so it's an element in a reducible representation for Clifford of B plus. And the Killing spinor equations, which I defined abstractly the other day, using some operator, etc., amount to these algebraic conditions, nonlinear algebraic conditions. So here, the AI, AJ are dual, the S sub I, AJ are dual bases of B plus, satisfying this relation. There's Gravitino equation, which was the expression, the formal replacement of parallel, of the spinor being parallel with respect to the spin connection, is given by this expression here. So pi minus is the projection into minus. So it means that for any element in B minus, I insert here this element, and this expression should be 0. And then the so-called Di Latino equation is equivalent to this. Any questions about this? This is recap, and hopefully now it's clear, because there was some debate the other day after the talk that these expressions may not be algebraic. So these expressions on a quadratic Lie algebra are algebraic, non-linear, but algebraic. If you replace the quadratic Lie algebra by a current algebroid, this is going to give you some complicated partial differential equation. Okay, but in this setup, this is purely algebraic. There's no. So my claim is that out of solutions of these equations, you can produce suitable Vertex algebra monomorphisms, embeddings. So another thing that I recall the other day, what I mentioned the other day, is that in the special case that the dimension of B plus is even and the spinor is pure, you can rephrase these Killing spinor equations in a much nicer way, which relate to more amenable conditions. The fact that you have Lie subalgebras of the complexification, and the fact that you have like more or less series of a moment map, even though this is not so clear. So in this setup, even dimensional B plus, eta pure, what we have, if we have a solution of the Killing spinor equations, equivalently is a decomposition of the complexification of B plus. So my Lie algebra, my quadratic Lie algebra is over the real numbers. So I complexify. The spinor is pure, gives me a decomposition into complementary subspaces. One is the conjugate of the other, and both are Lie subalgebras of the complexification of G. And the Di Latino equation, this, yeah, it's not what I'm saying. And it's a combination of both equations. And then the other condition is that this sum over elements in an isotropic basis, so the S sub I are in L, the S super I are in L bar, and they are dual bases. This sum, which is independent of the choice of basis, is minus the complex structure given by the spinor multiplying phi. Okay. And this quantity is a very interesting quantity in representation theory of Lie algebras, and I think the person who knows more about that is probably Raymond. So this is the first result I wanted to comment today. So if we have a solution of the Killing spinor equations on a quadratic Lie algebra, where the dimension of B plus is even and this spinor is pure, And furthermore, the phi which lives in B+, this element in B+, is holomorphic in the sense that it preserves L. Then we have an embedding of the n equals to 2 vertex algebra in the superaffinization of G with this level K, and central charge 3n. And the generator, so by the relations of the n equals 2 algebra, really the only thing you need to know, because the other fields are going to be generated by this, is an expression for the current J, for J. Okay, let me go back 1 minute, even if I see some people is copying things, but let me just go back to show you that this is all you need. Just a moment. In the expressions for the n equals to 2, right? Oh yeah, this is, yeah, from this, okay. You need more information from this. You need to know that this is a SUSY vertex algebra. Okay. It's not obvious, but it's true. It's true that this is the only thing you need. So let me know. I mean, there is for simplicity, I haven't stated things in that way, but there is a beautiful theory about vertex algebras with supersymmetry, which was developed by Raimundo Helwani and Victor Kax. And this n equals to 2 is an example of that. And when you see it inside that theory, then you see that the J actually generates. But yeah, here it's not obvious. I could have written down the expression for L, but for the J plus J minus, but it doesn't matter. I mean, the reason why I have written down this thing is because it gives us like a general procedure for trying to realize this sort of program that I was mentioning of constructing vertex algebra, interesting vertex algebra embeddings from solutions of the Killing-Spinner equations. And the idea is the following. The idea is the following.
A special value of K?
Not for this.
Is for any K?
Yeah, this is for any K. And but the K, only for K equals to 2, you can realize B2G super as fitting inside the Carroll-Durant complex of the corresponding group. So this is for any K, yeah.
There's some relation between the parameter and the n equals 2 and the...
No, this is for any. I mean, we have another result which is a bit more, there are more conditions, but this one is literally like that.
G super chapters, not BKG.
Yeah.
When you go to G super, you can feel the...
Yeah. Yeah. And the thing that is special about the level is that whether you can embed BKG super inside the CDR of the, so if your G is K plus K dual, then there is the question of if you take a group whose the algebra is little k, whether you can insert or embed this thing, the BK super, inside the CDR, and this is only for K equals to 2. Anyway, so the general, this is why I wanted to write this expression for the generator of J. The general picture will be if I have a solution of the Killing-Spinner equations, G phi eta, then my spinor, if it is non-degenerate in a suitable sense, in this case pure, is going to determine a bunch of tensors in B+. So tensors. I mean, in the best case, it will be just polyforms. Sigma I in lambda star of B plus 1. For example, if I have a pure spinor, one of these tensors is just I have EI, which EI, which is the Keller form, the Hermitian form. And formally, the generators for the algebra correspond to quantization of these tensors. So replacing the wedge product by the normally ordered product. And I have no general proof of this, but this is morally what you should do in order to produce embeddings. And this appears once and again in all the literature about these embeddings. I mean, you can see it very nicely in the work by Helwani, Sabsin, Ekstrand, in the case of spatial holonomy. Okay, so what we do is slightly more general. It generalizes a result by Getzler and also by Helwani and Sabsin, but let me not go into that. So to finish, I would like to tell you about this other case, which is very interesting. Do I have like 10 minutes or? Yeah, 15, okay. Yeah. So this case, so this is a bit more maybe for the experts, but still, I think this is interesting for several reasons. So the previous setup, embeddings of the n equals to 2, are more related to the general framework of mirror symmetry. Actually, in this work where we produce these examples, these embeddings, we prove that this can be used to produce pairs of complex manifolds which are non-Keller. The underlying manifold is the Hopf surface, and they are mirror in a suitable sense, in a sense that they have natural vertex algebras associated to them for each choice of complex structure. These vertex algebras have n equals to 2 embeddings, and there is an isomorphism between them which realizes the mirror involution. So this other case is more related to another question in physics, which is called holography. And I would like to comment on that. So what is this, the form Satas-Billy-Buffer? So there is a vertex algebra, which is very complicated. I'm going to show you what is. It takes 3 slides to show you the lambda brackets. So there is a vertex algebra called Satas-Billy-Buffer, which describes the algebra of symmetries of a 2-dimensional sigma model with target a G2 holonomy manifold. Really, what Satas-Billy and Buffer did was to observe that this was the right algebra of symmetries in the torus, in the flat torus. And then in a tour de force, Rodriguez-Diaz managed to prove that this is actually also the case for any G2 holonomy metric. And this is a very complicated paper, very hardcore calculations, etc. And then some years, I forgot to put the reference, but this is pretty recent. This is like 2015, I don't know, 17 or, and I think it's post-pandemics. So in this paper by Fisset and Gaberdiel, they propose a 1-parameter family of deformations of this Satas-Billy-Buffer vertex algebra, which depend on a parameter A, a complex parameter, and is suitable for describing ADS3 backgrounds in string theory. So what I mean here is that in the original picture by Satas-Billy and Buffer, they are thinking of a string theory compactified on flat Minkowski R3. So in the Satas-Billy-Buffer picture, they are thinking, or this algebra is related to compactifications of a string theory on flat Minkowski R3 times a compact 7-dimensional manifold with holonomy of the metric contained in G2. And then what Fisset and Gaberdiel observed is that this algebra has a natural 1-parameter deformation. Yes?
I have a question. The Satas-Billy-Buffer is a W algebra, and it's a special particular case of Hamilton reduction of particular level. Is there any other deformation that the fact that the W algebra always comes with the parameter that is the level of
I think what Fisset and Gaberdiel did in their paper is read your paper and realize, I mean your paper with Lázaro, and realize that there is this natural deformation. And this was already observed by Blumenhagen a long time ago in the 90s. But I mean,
it is the Hamilton reduction of the affine algebra. The affine algebra has a level. So the Satas-Billy-Buffer is a W algebra at a particular.
Okay. So let's.
I think
explain me all that.
I want to say cats and Guacamole.
Okay, explain me all that after my talk. I would like to know everything. So, what these people observe is that this is suitable for compactifying on anti-de Sitter. This is now negatively curved. And this manifold is no longer G2 holonomy, has torsion. G is part of a G2 structure, but with torsion. It has not holonomy of the Levitsky beta contained in G2. G2 structure. Let me put a phi, because it's the free form, which matters here. Phi is a G2 structure. It's a three form. It's a three form in T star M, which is with torsion. So in 7 dimensions, there are suitable three forms which reduce the structure group of the manifold of the frame bundle to G2. These are special. The other day I showed you an example. And a G2 structure is one which point-wise can be represented in the form I wrote the other day. And this thing carries a special class. I'm going to mess up with this, but I think it's type 0 over 6 times a star phi of phi. So the G2 structure determines a metric. And this has a Hodge-star operator. And there is a special torsion class. So in the G2 holonomy case, phi will be D closed and D star closed. In this case, there is torsion, and there is a special torsion class, which is given by this tau naught, the scalar class. And this tau naught is related to this parameter A. Okay, so let me show you the forms that has Billy Buffa. And as you can see, if you have any questions, you can ask Raimundo. So this is a presentation of the algebra, which is probably not the best one, because as you see, or you will see later, there is something funny about it. So the Satas-Billy Buffa vertex algebra is a special class of vertex algebra. It's called SUSY. And as a city model, it's going to be generated by 1, 2, 3, 4, 5, 6 fields. L is going to be Virasoro with a special central charge, which is depending on A. And yeah, and then the rest is not very illuminating. There is something interesting here. This is the first slide. So let me go to the second slide. So far, this looks good. It looks like similar to the previous expressions that we had before, in the sense that everything is linear in the phis, if I'm not mistaken. Everything is linear in the fields here. But let's go to the second slide. Then some funny things happen, because now some of the expressions are no longer linear in the fields. For example, this lambda bracket cannot be expressed in terms of the Lie conformal algebra per se. You need a vertex algebra realization of that, because then this normal error product appears here. And similarly for this lambda bracket, and similarly for this lambda bracket. I'm almost done. So this is the last lambda bracket. Okay? But the new thing, the thing that hasn't appeared in the general theory that I told you before, is the fact that these lambda brackets cannot be defined per se in terms of the Lie conformal algebra. You need some vertex algebra realization of that, and some normal error product. And there is even something more funny, which was understood in this paper by Helwani and Rodriguez Diaz, which is that for this presentation of the algebra, this is not even, the lambda brackets do not even close. You need to impose a relation, which is this relation here. And this is related to the fact that this is Hamiltonian reduction, and there is a much better presentation, I guess, from that picture, where you don't need to impose any relation whatsoever. It just comes from. Okay. Anyway, I mean, yeah, we were convinced that this is just a bad presentation of the algebra. You can do better. In particular, this G and L define West bars with this central charge, which is the form, is the central charge you would expect from a string theory. So in a string theory, you expect the central charge of the chiral algebra of the two-dimensional sigma model to be 3/2 times the dimension of the manifold. And this is the form by this parameter, right? Yeah. So now we take this specific quadratic Lie algebra, SU2 cross SU2 cross R, which is geometrically is like taking my 7 manifold to be the 3 sphere cross the 3 sphere cross S1. This is a 7-dimensional manifold. It can be proved that it carries no G2 holonomy metric whatsoever, but it carries one of these G2 structures with torsion and non-trivial scalar torsion class. And this is the explicit example. So you now take from this Lie algebra K, you form the dual, K plus K dual, with a duality pairing, and the bracket twisted by this 3 form, which is given by the 2 Cartan 3 forms rescaled by 2 parameters. So B1, 2, 3 are generators of SU2, of the first SU2, B4, 5, 6 are generators of the second SU2, and the generator of the R, the abelian part, is going to be B7. So I choose positive constants, L, S is 7. And now this determines a solution of the Killing-Spinor equations. I told you the other day that the spinor in 7 dimensions is the same as a 3 form whose orbit under the action of GLR7 is open in the space of 3 forms. And this is the specific form of the 3 form. It's a 1 form wedge omega, where the 1 form is given by this parameter C7. And then a 2 form little omega and a 3 form omega plus, which depend on all this. And I claim that this is a solution of the Killing-Spinor equations in this setup. The metric is going to be given by this expression, and the divergence is going to be given by the projection into plus of V7. So just let me take 1 minute to put this into the framework that we had. So recall that in this setup, I can produce a metric. So I take G, which is of the form K plus K dual, and I'm going to denote V plus to be things of the form V plus GV, where this G is this metric G, where B is in K. My endomorphism G is the identity on B plus minus the identity on B minus. The spinor for B plus, this is an irreducible representation of Clifford for B plus, can be identified with the 3 form phi. And the divergence, I'm taking this to be this projection into some number, and then the projection of B7 into plus. So this is the solution. And yes, to finish, this is the theorem which illustrates this fact that the way to produce these vertex algebra embeddings is to take the tensors given by the spinor and quantize wedge products in a suitable sense. So you define the following odd vectors, which are given by a basis, an orthonormal basis of B plus, suitably normalized and change parity. Then each element in this parameter family of solutions of the Killing-Spinor equations determines an embedding of the deformed attachability of a vertex algebra on the super-affinization. For this choice of parameter, where tau naught is precisely the scalar torsion class. And the generator is given by this by this expression in terms of normal algebraic products, which is essentially taking the 3 form, which determines my G2 structure, my spinor, and quantizing the wedges to normal algebraic products. And yeah, and there are, from the fact that this algebra, vertex algebra, is a SUSY vertex algebra using the theory by Helwani and GAAG, one can actually show that it is enough to determine, to show you the expression for this phi, and this determines the rest of fields in an algebraic way. So I think I'm pretty much done. Yeah, I have 1 minute left. So let me take that minute to tell you that the expectation, and there is a recent paper by Witten about that, is that the expectation, or at least my hope, my dream, is that this type of machinery can be used to mathematically understand some aspects of holography for these very simple backgrounds. So holography is a principle, is a duality in string theory, which tells you that supergravity on a manifold like this, or this, supergravity on a 10-dimensional manifold, where the Minkowski space is anti de Sitter, is in a sense equivalent to a suitable limit, of a conformal field theory on the boundary of the A3. But here the boundary of the A3 is 2-dimensional. So this is a 2-dimensional conformal field theory, and this can be encoded in the theory of vertex algebras. So morally, at least, this type of vertex algebra embedding should be able to tell you things about the conformal field theory dual. And there is a proposal by Witten about this conformal field theory dual, and it's a sigma model. It's a 2-dimensional sigma model. So maps from a cylinder into some manifold M. And this model this manifold is a modular space of ASD connections on a Hopf surface, which has geometry S3 cross S1. And yeah, I would like to finish with this perspective. And thank you for your attention.